My name is Milad Pourrahmani. I'm a graduate student at the University of California, Irvine. I do observational cosmology, and I use the Wolfram language to train neural networks to look for gravitational lenses, which are very precious as natural telescopes in the field of cosmology. Good morning, everyone. Thank you so much for coming here at such an early hour. My name is Milad. I'm from the Department of Physics and Astronomy from University of California, Irvine. Glad to see you here. So I do research in observational cosmology, and I'm going to spend most of my time during this talk telling you what the problem is rather than telling you how I solve it very easily with Mathematica. So first of all, probably most of you know what gravitational lenses are. For those of you who don't know, when you have a galaxy far away, like this one, it looks very small, and then you have a very massive galaxy in front of it, the light from this one would get bent by the gravitational field of this one and be focused on Earth. And it magnifies the image of this background galaxy. And you can see the equations that are governing gravitational lenses. So this is a very powerful tool because we can't build telescopes this powerful, and they are there for free. We just have to find them. The background galaxies would look like a few dots on our most powerful telescopes, and after they get lensed, they would look like arcs, like this image that you see over here, right? So what's so hard about finding them? Well, these are my favorite numbers. 10 to the 11 is one of my favorite numbers. So when you get 10 to the 11 stars, you form a galaxy. And the observable universe has 10 to the 11 galaxies in it. So let me tell you what that means. If you have an 8-foot straw, and you look through it, and if you could see the same way that Hubble Space Telescopes sees, you would see that image on the very right, this one, filled with galaxies. This was pointed at one of the darkest corners of the sky, and you see thousands of galaxies. But most of them are not important for my research because they are very tiny. They are just like dots. But the ones in the foreground that are larger are the ones that I'm looking for. So the galaxies that I look at so let me tell you how many galaxies I have to go through to look for gravitational lenses. So if you have 1 degree by 1 degree, so 1 square degree, you have 250,000 galaxies. So 250,000 images that you have to go through. And people in the past would look in regions that are highly probable to have gravitational lenses. Or they would ask, people by like in projects like citizen scientists and other projects like that, ask people to go through images and classify galaxies and look for gravitational lenses. That was the technique. So now we are trying to make astronomy autonomous because we have new telescopes coming that are producing 10 terabytes of data every night, 100 terabytes of data every night. And we can't handle that much information using manpower. We need to make things automated. So just letting you know how many square degrees there are in the sky, 41,000. That's very huge. So just multiply 250,000 by that number, and you see how many galaxies we need to classify. All right, so when you get these images, they look like this. So this is a cutout of a galaxy. Doesn't look like much. So one of the challenges that I had to face was to, in an automated way, change the contrast and the gamma correction and all sorts of things to make them, look something nice, and it doesn't always work. You get these white images, awful images. And then there's a really neat mathematical function that I use. I call it magic. You click that, And do you see the arc in that image? So that's the lens galaxy. So if I didn't adjust the contrast and the gamma correction and the brightness correctly, I would not be able to see that. And my code wouldn't be able to see that. So I use histogram transform, and that works like magic. So in other areas of computer science, they just average the mean, because you need to send normalized data to your neural network. But that doesn't work here. If you just normalize your data, you wouldn't see the arcs. So I use histogram transform to make the arcs stand out, and it works pretty well. So the problem is with neural networks and machine learning, you need thousands of examples. We do not have thousands of examples of gravitational lenses, so I have to make them artificially. One of the methods I use is this little applet here. So I have a collection of elliptical galaxies. So spiral galaxies usually don't form lens systems. It's elliptical galaxies that do, because they have more dark matter. By the way, it's not the mass of the stars that are causing the lensing. It is the dark matter that is causing the lensing. So it is very important, because we can understand dark matter better. So I can randomize this thing and form different lenses, and if I like it, I can store it and then do this. I do this 200 times, and then I do image augmentation, rotate them, flip them, move them around a little to increase that to a few thousand. And then the other technique, which I started using after I created this talk, was drawing. So I found this website that you can draw very similar to gravitational lenses very easily. And before this, I used this hardcore software called Lens Tool, which you have to use in Linux, and you have to code for it, and it's very slow, and it gives you perfect arcs that match physics. But that doesn't matter. It just has to match the geometry, and it needs to look similar. So this method combined with the drawing method works very fine for me to create these examples of lenses. And for the example of non-lenses, I have thousands of examples. I just select randomly from the data I have. All right. So a little about the neural networks, probably you know about it. You have convolutional neural networks. These were invented a long time ago, but we weren't able to use them because of GPUs. And you have convolution layers, pooling layers, and at the end you have fully connected layers that are basically looking for features in images. So my particular neural network has this particular architecture. It took me a while to find this one, because if it's larger than this, it would take a long time for me to scan the area that I have, which is just 2 square degrees. Sorry, 2 degrees by 2 degrees. It would take hours on a GPU. So I had to optimize to the lowest number of layers that I have. Do you have any questions about the layers, convolution layers thing? All right, all right. So yes.
Is that actually a hyperbolic tangent?
Yes, yes.
Okay. Can you very briefly describe why hyperbolic tangents are useful?
So if you don't have hyperbolic tangent, you usually use rectilinear, and then that's basically a cutoff. And I find that this is I think it looks like this.
Yeah.
So it's sensitive to negative numbers as well. I mean, you can shift the bias, but so it doesn't turn it into zeros and non-zeros. So it gives it more range. And I think the reason it works better in this case is because the lenses, so the arcs are a little dimmer, versus in cats and dogs, you have edges that are clear. All right. So does this work? Yes. So I was able to find a few lenses, and then I was just testing this. Some of these lenses were previously known, and the way I find them is not by asking, is this a lens or not? It's by assigning a probability. So I assign a probability to quarter of a million images, and then I rank them. So So I have two neural networks rather than one. The first one puts all the lenses in the top 5%, the most probable ones. So that's already really good, but not really, because that means I have to look at 15,000 images, which is still very difficult. So I have another one which specializes into filtering things that look like lenses, like spiral galaxies, because they have these arcs, and some things that I'm like, is that a lens? I'm not sure. I still have issues classifying them. Some of them are not clear. And as you see, some of them do not have a counter image, like this one. You just have this arc. And then you don't know if this is a lens or not. And one of the issues that I have here, I'm not using color information. I did not have access to color information, which was a mistake, but I have to finish this project. When you have color information, these arcs look red, and the foreground looks blue. So you can say, that's a lens. And if it's not, it just has the same color, etc. And sometimes you get these nice, lenses. Right? I want to share with you a little story about my hardwares. So NVIDIA was very nice enough to give us a free GPU. And my advisor was nice enough to buy me this gorgeous external GPU enclosure. So it was challenging to set it up, but after doing it for the first time, it's pretty easy. You just plug it in to your laptop, and then you connect your internet, mouse, everything, and then you just plug it into your laptop, and then you have to install the drivers for that GPU, which you can get from NVIDIA, and you have to get CUDA by signing up on NVIDIA, etc. And on Mathematica, I had no problem. All you need to do is to say, after doing all those things, you need to say, it's CUDA link, and then system information. So once you do that, you go to links, and then you go to CUDA, and there you can see your GPUs. So I had one for my laptop, and I had one which was my external GPU, because I really wanted to know which one is which when you are using target device to train your neural network. So when you are training your neural network, I think it's automatically set to CPU, if I'm not mistaken. But then you can say GPU 1, GPU 2, etc. And it's way faster. GPUs are made, neural networks has to be applied on GPUs. It takes, so running my code on a GPU is 170 times faster than running it on a CPU, for instance, right? And I'd like to thank NSF for supporting my research, NVIDIA, and the Wolfram community for answering my bizarre questions on Stack Flow. And thank you so much. If you have questions, I would be glad to answer. Yes.
How do you distinguish between diffraction patterns, like circular diffraction patterns?
So we do not have those for galaxies. We do have them for stars. And it's not circular diffraction patterns. You get those sometimes, but it's mainly spikes that extend many arc seconds. And sometimes I have images, and there's a line going through them. And so I have to filter those out. So only stars have those. And I had to kind of create extra stars, separate them, rotate them, augment them, to teach my neural network that you shouldn't classify stars as lenses.
How many lenses were already known? How many have you been able to discover?
So I showed you a few examples. There were, we wouldn't say known. We call them lens candidates because you need to do a lot of research to prove that they are actual lenses. Sometimes they're obvious, but for many cases they are not. So there were, I think, 60 lens candidates in the Cosmos field from Hubble Space Telescope. And then, I was able to find majority of them. Some of them fall beyond the window I'm looking. And then many of them did not look like lens galaxies. And they were lens galaxies, but not in the band I was looking at. So in this color space, they wouldn't look like lenses at all. So after doing that, there are like 50 that look like lenses in that band. And then on top of that 50, I was able to find an additional 12 or so. Yeah. Yes?
I have a dumb question.
Please.
On your first slide, you had the 10 to the power 11, you had it listed 3 times, and you explained it twice.
Oh, I forgot. I was going to ask.
What was the third one?
Well, what that? The first one was, do you know how many brain cells do we have?
Oh,
It's 10 to the 11.
okay.
And I was, yeah, it didn't have anything to do with my talk, but I like that number a lot. Yes.
How many total cores do you have on your NVIDIA box?
So that GPU, I think, has 3,500 CUDA cores.
Like a GTX 1080?
Yes, yes. It's Titan XP. Sorry, it's Titan XP GTX. Yeah, yeah. Yes.
How much work was it to construct the neural network that worked?
Oh, I started my research learning TensorFlow, and then I got introduced to Keras. My code was, very long, and then, it became smaller, and then, Mathematica released the machine learning package, and then I wasted so much time. It's pretty easy, yeah. Like everything is in a notebook right now. And if you want to scan the entire sky, I can do this test on Mathematica and then, shift it to TensorFlow or work it that way. But I don't see any reason because it's fast enough. So now it takes me 200 seconds to scan 250,000 images on that GPU. So that's doable. Yeah. Does that answer your question?
Well, I was wondering how much time you invested, and actually, you said you had to optimize the neural network to make it fast enough. How much time did you spend experimenting until you arrived at the neural network structure that worked for you?
A lot. I would say maybe 6 months. Yeah. But the efficiency for graduate students is not that high because there are meetings, there are classes, there are other things. So that's probably why. Yeah. Yes.
Did you classify your original galaxies as oval-shaped galaxies or spiral-shaped galaxies? Like, did you do any previous classification just to get your galaxies?
I tried a lot of things. So I had a neural network that would classify stars, spiral galaxies, elliptical galaxies, and all sorts of things. I tried different methods. The best one that worked was having 2 neural networks, and then you have lensed versus non-lens. And then you do that again. But then, I take my training data randomly from the cosmos field, from these images. So when you go to the second, so when I reduce 250,000 to only
No. You said like lenses only occur for oval-shaped galaxies,
yes,
and they don't occur for like spiral-shaped, right?
yes, they do, but they're very scarce. So I'm not focusing on that.
So your original data set excluded the spiral.
Yes,
Okay.
yes. Good question. Yes.
How often do you retrain your network? I assume there's more data in the world all the time.
So right now, what I was trying to do was a proof of concept, which, we already knew there are 60 lenses here, and we want to see if we can find them. And without using those in my training data. And then, to scan them to find more lenses, which I'm going to try, in the upcoming week, is to use those lenses and look for, new lenses, see if I can find anything. But, after this one, I'm moving to new fields. And then, you have to, I think you have to especially train a neural network for a particular telescope, for a particular camera, and possibly for a particular filter for the color bands. unless there's a high contrast between your arcs and your foreground galaxy, then possibly. But the resolution is very different, and the color space is very different. So I think you have to.
Do you think you could add more layers to account for that?
Yeah, I think so. So the challenges of my research, unfortunately, it's not machine learning, it's generating the data. And I use Lens 2. I don't know if anyone is familiar with that. You're very limited to what you can do. It wasn't designed to generate thousands of examples, and it only gives you arcs, and you have to superpose that against galaxies, which I did. That's why it took 6 months for me to try that. And there aren't that many lenses that look like that. So later I figured out you can just draw them. That works perfectly fine, just to draw them. Now I have to find a nice way of saying that in my paper. But I don't know what the referee would say. Yes.
An astronomical question.
Yes.
Can you infer the shape of the background galaxy from the image?
So with neural networks or in general?
General.
Yes. There are special softwares that do that. I mean, that's why we are looking for them. So I'm not doing that part. There is another person in my group that does just that, because this would help us understand the evolution of galaxies. And then there's this really cool thing, which was first observed a few years ago. You have a supernova happening in the background galaxy. And when that happens, it's huge, because you get images of the supernova in one arc first, and then you get the second image later, maybe a week later, maybe a month later, and that helps you to probe the cosmos and the dark matter in between, and then know the distances. Is just really powerful. So we are trying to identify these lenses. So we have telescopes that are looking at the photon count. Basically, they count the photons, and then we want to see when they happen. So we will shift our telescopes to them, because they're very, very precious to probe the cosmos. So that's another way of that you can extract information. And then, reconstructing those images helps you understand the dark matter distribution around the foreground galaxies, and then also evolution of the galaxies, because you can see further back in time and in space. Good question.
You have
Yes.
the background image and the lens image. You can infer the distribution of dark matter.
You have to do a lot of hand waving, and then there are, some people are concerned that there's some issues here. But yes, because you know how much light you have from the foreground galaxy, from the background galaxy, and then you know what type of galaxies they are. Their redshift, etc. So you know how much dark matter they should have. Their relative distances. So you can kind of figure out how much dark matter there is around each one of them. You can, but then you're relying on one theory after another, and then suddenly you have 50 theories back to back. So that's kind of concerning.
What does the distribution of dark matter look like? Is it distributed similar to the rest of matter?
No.
Galaxies?
This is how it looks. This is a galaxy, and there's this uniform giant ball of dark matter around it, and this is how big the galaxy is compared to that. And that's why when you look at the rotation curve of the stars around the galaxies, they kind of go higher and higher, and they plateau. And it doesn't matter how far away you go from the center of the galaxies. The stars on the spirals and the far ends of the galaxy are rotating with the same speed. That doesn't make sense. And that was the first hint to dark matter. And the gravitational lenses were kind of the proof that, hey, there's something going on here. So even if you have 5 times, 6 times more distant from the center than the ones that you see on the edge, they still move with the same orbital velocity around the galaxy.
And is that why the spiral arms are coherent? They don't sort of spin out of. If the inside was spinning much faster, then the arms wouldn't exist. They would just kind of swirl away, right?
I think so. The dynamic is, the fluid dynamic of galaxies is very complex, and they just do simulations nowadays rather than thinking about it how it works. But yeah, I'm not an expert in that area, but I think so. Right? Well, thank you so much for coming. Appreciate it.